In this lecture, we will see how can we make a single-phase induction motor self-starting. From our previous lecture, we came to know that if we have a stator configuration like this way, which is supplied by a single-phase source, and if we place a rotor which has a squirrel cage type configuration, after giving the supply, the motor won't be able to start. But if we provide a force in any direction, motor starts rotating in that direction. Why it happens? It was described by employing double field revolving theory. So it is for sure that this type of motor is not self-starting. We need to give an external force to start the motor. How can we make this type of motor self-starting? We described a split phase operation where we plotted this configuration. I hope you remember. If we have a phase current here through this winding and another phase current through this winding, if these currents are 90-degree apart, then there will be a creation of rotating magnetic field, and that rotating magnetic field will have a magnitude that is phi m, which is the maximum amplitude of each magnetic field. That means in the x direction magnetic field and y direction magnetic field, we are considering both are having the same maximum amplitude. So in addition to these windings, we need to have another winding. In literature, this extra winding is named as auxiliary winding. Auxiliary winding. And this winding is named as main winding. This auxiliary winding is used for starting the motor. As we know, if we use this auxiliary winding through which a different phase current will be flowing, that will create a rotating magnetic field, and eventually that will give an initial torque in a particular direction to the rotor, which will start the motor. That's why this winding sometimes it is called as starting winding. Now the question is, how can we split the phase so that we can have currents with different phase angle difference? There are three techniques commonly used to start these motors, and single-phase induction motors are classified according to the methods used to produce their starting torque. The three major starting techniques are: number one, split phase winding. Split phase winding. Next, capacitor type winding. These capacitor type windings have three types. Number one, capacitor third induction run. Another type is permanent split capacitor, and the third type is capacitor start capacitor run motor, and the third type is shaded stator poles. We'll describe all these three types. All these three techniques have similar theoretical basics, that is to make two magnetic fields having a particular phase angle difference so that we can have a rotating magnetic field in any particular direction, and an initial force can be given to the rotor so that it gets starting torque at the very initial moment. Let us discuss split phase winding first. A split phase motor is a single phase induction motor with two stator windings. One will be the main winding, another will be the auxiliary winding. And the configuration will look like this. Let me draw it here. This is the equivalent resistance of the main winding Rm and the equivalent reactance of the main winding Xm. And another winding, that is the auxiliary winding. This will be connected through a centrifugal switch. How it operates, I'm coming to that point later on. So this is the auxiliary winding JXA RA. Here the supply voltage will be provided VAC. The current through this will be the IM, and the current through this will be IA. And we have the rotor. This motor is constructed in such a way so that the main winding contains higher reactance than the auxiliary winding. How is it done in the industries? In the auxiliary windings, engineers generally use thinner wire, and in main winding, the thicker wires are used. In this way, we can have a higher resistance by reactance ratio in the auxiliary winding than the main winding. As you know, in thick wire, the resistance value is low and the reactance value is higher. While in the thinner wire, the resistance value will be higher and the reactance value will be lower. So RA over XA is greater than RM over XM. This relationship is maintained. By maintaining this relationship, the current in the auxiliary windings will lead the current in the main winding. Things will be more clear if I draw the vector diagram. Suppose this is VAC. If this would be purely inductive, then current would lag than VAC by 90 degree. But we can see this is not purely inductive. We have internal resistance in the main winding coil. So current will be lagging as this Xm value is higher, so it will not be 90 degree lagging, but it will near to the 90 degree. So this is the current for main winding, that is Im. And the current through this line, that is the auxiliary winding, that has lower reactance but higher resistance. So this current will be near to the VAC line. So this current will have a vector diagram in this direction. And the total current I is the vector summation of these two currents. So this will give us the total current value I. Let's go to the next page. If the angle difference between these two currents is theta, then if we consider IA equal to Im sine omega t, we are taking IA current as a reference, then Im current will be I small m sine omega t minus theta, because this is theta angle difference and Im current is lagging behind Ia, so omega t minus theta. As main winding is placed in this direction and auxiliary winding is placed 90 degree mechanically apart from the main winding, so the flux that will be produced here due to Im, that will be phi m, and flux produced by Ia, that will be denoted as phi a. So we can say phi a can be denoted by phi m sine omega t. This is small m, and phi m, that means magnetic flux in the main winding, is phi small m sine omega t minus theta, because the currents are having theta degree angle difference. Now these two magnetic flux will have sinusoidal in nature, and they are having theta degree angle difference, electrical angle difference, and they are placed 90 degree apart mechanically. So if we plot for a different omega t condition, for example, for omega t equal to 0, for omega t equal to 30 degree, for omega t equal to 45 degree, we'll find that the summation of these two fields are having different values at different position, but they will be rotating in nature. So they will be having different values, and they are not uniform, as the angle difference between them is not exactly 90 degree. If they would have 90 degree angle difference, then we could get uniformly rotating magnetic field. As they are not having the exactly 90 degree angle difference, so there will be a creation of rotating magnetic field, but that will not be uniform. I want all of you to plot this using this equation and to check whether they're producing a rotating magnetic field or not, and the magnitude of the rotating magnetic field is uniform or not. As there will be a creation of rotating magnetic field, so the rotor will get an initial torque in the direction of the rotating magnetic field. And what is the principle? Principle was described while describing the rotation of three-phase induction motor. The main thing is that rotor can see that it is experiencing a rotating magnetic field around, so it will try to catch that speed. Now, what is the function of this centrifugal switch? The centrifugal switch is generally connected, but it disconnects once the rotor gets a certain amount of speed. So once the rotor gets an initial torque, rotor starts rotating, then centrifugal switch gets disconnected with the main winding connected. This is the main winding connected. As we know, if the rotor gets an initial force in any direction, rotor keeps moving, though after some time this auxiliary winding is disconnected, rotor will keep moving. When the motor is switched off, this centrifugal switch will be connected again. When we'll switch on the motor with the help of auxiliary winding and the main winding, the rotor will get some initial thrust in a particular direction. Rotor will start rotating. Once rotor gets some speed, the centrifugal switch will be disconnected. In this way, rotor will keep moving. In this way, by employing split phase winding, we can make this single phase induction motor self-starting. Let us draw the torque speed characteristics curve for this type of motor. This is the rotor speed nr. This is tau r. We know without the auxiliary winding, the torque speed characteristics curve looks like this. You can recall this curve from the previous lecture. We can see initial torque or starting torque is equal to 0. That's why with main winding connected, the motor won't be able to start as starting torque equal to 0. But when we connect this auxiliary winding, there will be a creation of non-uniform rotating magnetic field, which will give an initial starting torque. So with auxiliary winding connected, the torque speed characteristics curve will look like this. Now, what is the resultant torque speed characteristic? Initially, the auxiliary winding will be connected because centrifugal switch is connected. So the rotor will start with this amount of starting torque, tau s, and it will attain some speeds. After attaining a certain amount of speed, for example, this amount of speed, the switch is disconnected. So once the switch is disconnected, it will come back to the torque speed characteristics curve of the main winding only. So it will start following this curve, and it will be having an operating point here if the load that is connected is having this amount of value. So this will be the operating point. So the resulting torque speed characteristics curve will look like this. This point is synchronous speed. We will continue with other types of single phase induction motor in the next lecture. Thank you.